What's up, YouTube? In today's video, we're going to be looking at C# lowering. So like higher and lower, lowering. Essentially, it's an idea or a concept wherein the C# compiler takes our code, the code that we write, and it lowers it to a lower language version. That's not exactly correct, but that's kind of like how you want to see it. The C#, the .NET runtime has not essentially changed since .NET 2.0. That's not to say the runtime has not changed. From a language perspective, it has not changed. Of course, lots of changes have occurred since .NET 2.0 in the runtime as well, mainly optimizations and such. But they're not adding on any functionality, if you will, any new language functionality at the runtime level. All of the new language features that we've had in C# since then have been either library features like link, Async-Await, TPL, task parallel library, and then there are other language features that are implemented as a C# lowering technique. Why is it important? It's important because, well, you could be a C# programmer and not know it exists. Or if you want to kind of dig deeper, kind of go under the hood, you can learn about the code that is being written on your behalf, right? The code that you write in C#, what happens to it? Especially if you're looking at sometimes performance issues, a lot of them can be seen or discovered by understanding the code that you write and the code and what happens to that code. What is going on under the hood? Because you think you're writing this one line of code, for example, but it's not one line of code. And we'll see some of those examples as well. Some of those things are pretty shocking. That's not to say that you shouldn't use those features, but be cognizant of those features. So it's important to get that sense, right? The bigger your worldview of things is, the more informed you are when you, in this case, when you're writing code, and especially when stuff goes wrong or you can't quite explain why some things are slower, for example, or whatever. So, is this something being boxed or not boxed? Or is a class, instance being created or not? That sort of thing at the code level, right? So it's important from that perspective. We work at a Visual Studio level, meaning we're writing code in a C# code in Visual Studio, and that's, for the most part, most people's worldview of things kind of stops there. Under Visual Studio is the Roslyn compiler, the C#/VB compiler. So the code that we write is then compiled by Roslyn, which is a new compiler, a C# compiler, written in C#. The previous C# compiler was written in C++, C++. So the new Roslyn compiler has, of course, done some huge improvements with regards to performance. Believe it or not, the Roslyn compiler actually is faster than the older C++ compiler, not because C# is faster than C++ in these kind of things, but because they've learned. It's a completely new redesign. It's a huge topic, so I won't go into the details of that. But essentially, they're using immutable data structures and such, so you can have multiple threads partying on the same data structure and compiling things and doing a lot of work in parallel. So essentially, the parallelization or capability has given the Roslyn compiler that additional advantage. And of course, Roslyn is also surfacing a compiler as a service feature. In other words, it's got an API, and we can use that API actually in C#. And a lot of the Visual Studio analyzers and a bunch of other features in Visual Studio are using the Roslyn API to give us like code completion, refactorings, that sort of thing. At runtime, so we have two compilers in most managed languages. There's the compiler as we know it, and then there's the JIT compiler, the jitter, the just-in-time compiler, also formerly known as the jitter. The just-in-time compiler essentially takes, so the C# compiler compiles your C# or VB to IL, intermediate language. That is kind of a human readable assembler, if you will. It's not quite assembler, but it's very human readable. And then that, when you compile your code and you see an exe or a DLL, that's actually IL. When you run that executable, that's when the jitter just in time compiles methods that you're executing. And of course, if the methods call other methods, it might have to compile that method as well in order to compile this method. But it's not going to go down too deep. It's going to be sticking to just as much as it needs to compile, just-in-time compiler. The jitter takes the IL and compiles it down to native code. And the jitter has intimate knowledge about the environment, the operating system, the hardware, and so when it compiles the code at just-in-time, it has some advantages over, say, a compile language like C++ or Delphi that compile to native code on your developer machine, if you will. Under the jitter, we have the .NET Runtime. And under the .NET Runtime, we have the operating system. And under the operating system, we have the hardware. So by the time our code actually runs, it's so many levels, deeper than where we are at sitting at the Visual Studio aspect. At every level, there are certain things we gain and lose. They're not compromises, but they're just some things that we don't have direct access to, for example, or there's some nuances between these layers. We'll just talk about that briefly. So, for example, when I started with Visual Studio, with .NET, I was working with the SDK directly in the command line compiler, and I was using a feature called modules. Now in Visual Studio, you don't have access to modules, even though the C# compiler actually understands modules. We don't have access to it. And that was sad because I came from the perspective of understanding how to use modules. And if you look at the slide, you can see that an assembly is comprised of modules, and modules can have multiple classes. The way we see things today in Visual Studio, through Visual Studio, is that an assembly has classes. There's no modules. Yet the C# compiler actually supports modules, but we don't get access to that through Visual Studio. So Visual Studio is not giving us that feature, it's not surfacing that feature. So that's kind of what I mean by there are certain nuances, if you will. Now Roslyn, the C# compiler, as you can see, has its own nuances. Some things are not bad, they're just things you should probably understand. One is it's the C# or /VB.NET language compiler. Ints, the C# int, lowercase int, is really mapped to int32. Long is mapped to int64. The lowercase string is mapped to string. Many times I've asked people, if they what's the difference between the lowercase string and the uppercase string, or the int and the int32, and they get confused. The int, lowercase int, is a C# language thing. The C# language compiler has to compile C# language to work on the .NET framework. The .NET framework doesn't know int, it knows int32. So every language has some sort of a mapping, if you will. It has to compile the language to something that the runtime understands, which is IL. So int and long and string and all these things that turn blue, but in the default color scheme, they're actually special. There's a mapping certainly, but they're also special. They're called primitive types, and primitive types in .NET mean that the C# compiler, I don't mean .NET in C#, the C# compiler has intimate knowledge about that type. I won't go into the details of that, but it's not just the mapping for the primitive types. The compiler has special treatment for strings, for ints and longs and such. But nonetheless, there's a mapping between these. And then so in C# we have access modifiers for methods and classes. Typically, most people just say the method is public, protected, internal. But in C# you also have the ability to mark methods as protected internal, meaning both protected internal. But what is that protected internal? Is it protected or internal? Or is it protected and internal? Now the runtime supports both. So from a runtime perspective, by runtime I mean the .NET runtime, it supports both ideas. In C# language, however, we only have access to one of those. So the thing is, which one is it? Is it protected or internal, or is it protected and internal? Unfortunately, it is protected or internal. I say unfortunately because I've never had this need, but I would have loved it if I had the ability to say this method is protected and internal, not or, because Why would I want to make a protected method accessible to other classes? Right, but protected and internal will say this protected method is accessible only to descendants in this assembly, which I think is a little more beneficial than saying this method is either protected or it's internal. So other classes can use it in the same assembly, or it's only descendants can use it. Anyway, so it's up for debate, but that's another feature. So there are things that the .NET Runtime supports, but the C# language may not. Sometimes there are, of course, good decisions from a language standpoint. So to keep in mind that we are working in C# as a language. That language is sitting on top of the runtime, and the runtime has its own capabilities or own rules, if you will, all its own things that you can and can't do. And on top of that, the C# language compiler or the C# team has decided that the C# language will not allow certain things, right? So there's that nuance, so there's disconnect, if you will. As you can see on the slide, CIL is the intermediate language, IL, common intermediate language, or IL as we know it normally. It's a stack-based language. It does support protected and internal instead of just protected and internal instead of protected or internal. In the runtime, you can throw anything. In other words, I can literally just say throw a new string or throw my object, where my object is not a descendant of exception. The C# language actually will not allow that, which is good. It's a good thing, but it won't allow us to do that. So we can't throw a string. But the runtime has no constraint of that kind. Then the runtime allows us to overload methods based on, so we can differentiate overloads even by return type, which we can't do in C#. Which sometimes I wish we had that feature, but I'm not sure that it would be a good thing. But because I'm not used to thinking in those terms, I'm not seeing the benefit, because you always find ways around, and then you say there's no benefit to that because I already know how to do it like this. But just to highlight the fact that at the runtime level, the runtime is able to distinguish overloads even based on return type. So in other words, only if just the return type has changed, it could be considered an overload. But in the C# language, we don't see that as an overload. Right? You can't have the same arguments for two methods and say that's an overload. Then the runtime supports global fields and methods. So like in Delphi, all methods didn't need to be a part of a class. You could have methods that sort of just stood by themselves, right? They were global. In C#, they decided not to give us that feature of having global methods and fields. We can have statics, but they're within the class, if you will. But they're not kind of just by themselves. But the runtime supports that, so it's not like the runtime doesn't, the language does not support it. And as I mentioned earlier, the runtime has an understanding of modules and assemblies, whereas in C# we only have access to assemblies, no modules. Now, because Roslyn is an open source compiler, you can go to the GitHub repo and look at the source code, which is a pretty interesting thing if you're so inclined. But one of the folders in the compiler's source code is lower rings folder, and you'll see like there's a bunch of lowrings in the C# compiler source, and just by the names of the classes you can tell what kind of lowering they're doing. So that's the list of the classes there. We're not going to be talking about all of these things. We're going to just be talking about some of them. All right, so let's go switch to some. Now the jitter also has some optimizations and also does some lowerings. So I said earlier that the jitter has an advantage of understanding the environment it is running in and the hardware and the operating system, and it can compile code just in time to gain some advantage over languages like C++ and Delphi that are native code compiled from the get-go. And there are some optimizations also that happen at JIT time. So the jitter is, of course, having to balance between how much time should I spend trying to produce the most optimal code, because we are trying to run the application, right? So it has to, there's a sort of a tension between the time it can spend to optimize and how quickly will your application actually start, and how quickly will that method execute that first time. But there are some optimizations that occur, such as loop unwinding or unrolling, we call it. imagine you had a loop in your application where the compiler, the jitter, could say, well, I know by looking at that code here, it's a matter of calling the same method so many times. The stuff inside the loop, not method, maybe that chunk of code so many times. And it can switch let's say if there's an I and you're using the I inside of the loop, then you can say, okay, the first time is a 0, 1, 2, 3, and so on. The reason is that in assembler, the loop is a jump. It's like, go do this, jump back, do this, jump back. Jumps are expensive. So if the jitter can remove the jumps, assembler jumps, then it's going to be faster. So loop unrolling or unwinding is essentially this idea where you can rewrite that same method so many times, even if it's like 100 times, it will write that line of code 100 times with the change for each call to the method. Because there's a balance again between how much code should I produce, where it bloats the size of code in memory versus the speed, right? So, and then there's also a lowering step at JIT level, right? Just so you understand the stuff that's going on there. Okay. Now RyuJIT. RyuJIT is our new JIT compiler. I'm not sure if that's the right way to pronounce it, RyuJIT, but I haven't seen anywhere where some people have the right pronunciation for it. The RyuJIT compiler, as you can see, it predates .NET, which means it was actually envisioned, they started working on it even before .NET. Of course, in the very first versions of .NET, and RyuJIT is fairly new, it's probably like 2 years old maybe. And in terms of in production, but it has been a long time in the making. So before that we had another JIT compiler, but now RyuJIT is sort of it produces faster code, and it's cross-platform and such, as you can see here. So it supports, the original was designed only to support x86, but today it supports x86, x64, ARM32, ARM64. It's fully functional on Windows, Linux, Mac OS. Which is pretty cool, because now as C# programmers we can compile our code on the platform, and our applications can run on that platform as well. And languages like Java have what they call a hotspot optimizing compiler, which is essentially, we imagine that the jitter, after it's compiled the code, is watching execution as to, let's say you have a conditional statement, and most times it goes through let's say the false path, but it didn't know that. And so of course, to first check for the true and then go to the false is a performance problem, because again there's a jump, a conditional, and it has to go to another place, and from an assembler standpoint. So the Java hotspot compiler could recompile that code. So hotspot meaning in terms of performance. So it's watching the code execution, and it finds if there's a hotspot anywhere, it'll try and see if it can optimize the code to remove the hotspot. So the hotspot is also the most frequently used piece of code, and if it can optimize that just a little bit, you get a huge bang for the buck. In C#, what they've introduced in .NET 3.0 is a tiered compilation. So as I said before, there's a tension between how much time to spend trying to optimize the code versus how quickly can I have your application running up and running. So what they decided to do in .NET is the tiered compilation, which is get that code up and running as fast as possible, then keep a watch on the code and the execution paths, and start to optimize the code, recompile the code more optimal, and then swap out the previously compiled code for the newly compiled code, right? So that's the tiered compilation. That's a feature they introduced in .NET Core. So I think I said .NET 3.0. No, it's .NET Core 3.0. So moving forward, all .NETs will have that feature. So I've got a bunch of projects here, and the first one I'm going to show is the simple one, which is cast and const. So these two ideas, cast and const. So in this case, this project is just the cast versus as, and it's just to show you what goes on under the hood. So at this point, for example, I've got this immutable class, and this is also another thing that's going to get lowered. So you'll see the lowered version of this class. This is an immutable class. It's using this feature in .NET that we've got. We could always build immutable classes in .NET. The sort of the syntactic sugar, if you will, for defining a property like this, that's a read-only property, is new to .NET 7. I think they introduced it, or maybe was it 6? I forget now exactly, but yeah. So we'll see the lowered version of this class, but this is an immutable class, and this class is being used in this part of the project here. And you can see it's calling this method display premium with this new instance of this class. And then over here, it just calls that. So in this case, it's expecting an object, and then we are casting the object with 2 policy details. The other option is to do an as. I don't know what your preferences are. Do you normally do an as, or do you do a cast? Okay, so when we do method design, and I've already talked about this in my programming with intent video. If you haven't checked that out, please check that out. There's a lot of things I talk about with regards to method design in that video. But yeah, I prefer cast. There's a big reason for that. It's nothing to do with speed or performance, but certainly that's also a benefit. So now I'm going to compile this, and let's look at the IL. Okay, I didn't set up my... So IL, the way you discover IL is through a tool called IL-DASM. And if you don't know where it is on your machine, then you can find that. So what I'm going to do is I'm going to pull up the command line, the developer command line. And this tool is quite handy. You haven't used it, but you can also ask this tool, where is IL-DASM? So you can say where IL-DASM.exe. You have to put in the exe at the end. So it tells me it is over here. Right, so without me having to search especially when you're using different versions of Visual Studio on the same machine, it could get confusing. So I'm going to copy that. So and I'm going to show you how to set up an external tool in Visual Studio. So I'm going to add a new tool. I'm going to call it IL-DASM. Now, if I wanted to make this M to have the underscore when I go to the menu system, then you put an ampersand in here. Right? This has been in Windows for many years. So I'm going to paste in that command there, and the initial directory I want it to be in the binary directory of the current project. All right. So if I do this, now I should be able to do Alt-T-M. That opens up. What is this? I don't know what that is. And then Control-O will open up the open menu option here, and then I'm going to point it to this exe that I just compiled, the cast versus as. Okay, now you may not be familiar with IL, but I'll try and explain it. It's fairly simple. Okay, so the first thing I want to show you is, okay, this is IL. I want to show it to you here because this may not make sense, because it's probably easier to see this in C#, right? So there's another tool that you can use, and as I said earlier that there are 2 tools that you will be using, and there's many more. I'm talking about the free ones. So there's IL-DASM, that's part of the .NET framework itself. It gets installed on a machine, and there's a website called sharplab.io. So I'm going to copy this code. I'm going to paste it into sharplab. Right? So I'm going to paste it here. So that's the code that we want to see, really, right? And what it has done is it has compiled that code. Now, this is not the tool. The purpose of this tool is not to show you the lowered version. The tool's purpose is completely different. But I'm using this tool to show you some ideas or some things about the lowering. So what you can see is this class here, policy details, has been compiled here. This is the compiled version of this class. And you can see that they're using a backing field. This is just a variable, a local or a private variable. That's this name. Now that's another thing in C#. The C# compiler itself does not allow us to start like variable names with greater than, less than, and I believe underscores and stuff and things of that nature. But it doesn't allow us, but the C# compiler actually understands them. And so when it creates classes on the fly, it uses those names as the starting point, so there'll be no collision between our class names and its class names, the ones it produces on the fly. So this is a class name that is produced on the fly. Variable name is produced on the fly. It's a private read-only member. It is initialized in the constructor, and then in the getter of the method, of the property, it returns it. So this is how we would, if you were to do this by hand, that's exactly how we would implement this property, a read-only property. I distinguish between get-only and read-only, because now we have read-only properties, we have get-only properties as well. So we write the code this way. So this is just, you know, syntax sugar. It allows us to write code simply, but behind the scenes, the lowering aspect will lower the code to this, and this is, you know, C# 1.1 or 1.10, right? It's not something new to C# 7. It's just, this code just works anywhere. So that's what lowering is doing here. Now, as regards the cast versus the as, I'm going to use ILDASM for that. So I already had ILDASM opened up here, but I'm going to go look at the program class and specifically the display premium. Now this is IL. It's not the best tool to look at IL for, but what you're going to see is the method display premium. It's got one argument, and so it starts off saying load this 0 to the first argument, so 0 is the first argument, and then do a cast class operation on to this. Store that result in location 0, then load the thing from location 0 and call the method policy details.get premium on that policy. It's a virtual call. So there's a call and there's a virtual call. Now there's some reason, historical reason in the C# compiler where certain calls, even though they're not virtual methods, the IL will still use the callvert thing. It was so far back in the C# lifetime that I've forgotten why exactly that's there, but it's not to say that the call word is a slightly slower calling way to call a method, even though, especially when the method is not virtual, but that's what's happening here. The call here is doing a console write line, so that's the call, or you do a call word. So either of these two are calls, but you can see here is using the cast class operation. Right? This is not a loading concept. I just want to introduce you to IL like this. Okay, so now let's look at the as version of it. So I'm just going to recompile this with the as instead of the cast here. So it's Alt-M and Control O will open up the folder, open up the assembly. This time, when I look at the display premium methods IL, there'll be a slight difference, which is saying is inst, right? Now the thing is, you're not seeing I haven't written the code correctly in this case. When I do an as, you must always check to see. So this is inst is different from cast call. Let's actually just fix that. So typically what you would see, what you would do in your code would be here, you say this and you say if, you know, policy details is not null, because you must, if that's what you plan to do with the as, then you would want that. So it's conditionally, right? So now I'm just going to build this, open up the thing, open up the exe, and look at the display premium again. Okay, so now you see the IL that's supposed to be happening. So here again, you're loading up the first argument. You're calling the isInst method. You then store that here. The result of that, you load that again. You load up a null, so you can do the compare. And this is a form of compare in IL, one of the forms of compare in IL. And then just store the result of that in location 1, load the location 0, 1, and if it's false, then jump to 001E, so we jump here, exit basically. But if not, then do the callvert, do the call, and so on, right? So there's a bit more code here. Now it's not a performance difference here between as and cast. That's not the reason I'm not in favor of cast. It's what I call programming with intent. Show me your intent. What are you saying here? We'll get down to more detail in method design when I make a video on just method design. But if you're interested, there's another video I made earlier, a couple of years ago, called programming with intent. That entire video is essentially method design. but not so focused on that. There's many other things, so we might want to go look at that. All right, so now that this introduction has been simple, I'm going to switch to another project here on consts and default values. Just let me make this the default project and open this file up here. So we know constants, we know defaults, but so what's the deal here? So if you look at the lowered version, yes, let's just examine the code here. We got a constant defined called renew period is set to 180. We're using it over here, and then here's a method that has a default value set up to be 5. So let's look at what happens to this code. All right, so I'm going to compile it. Alt-T will open up LASM. Alt-Control-O will const. I thought that bin should have taken it there. Maybe I used the wrong one. Okay. All right. So now, actually, this will also show up pretty nicely in SharpLab. So let me show you this in. Actually, left myself a little message here. Show this in SharpLab. Okay. All right. So the constant is defined here, but it's appearing over here. Right. So at compile time, constants are baked into the call site. Constants are baked into the call site at compile time. So by the time you finish your compiling, wherever you use that constant, that has been replaced by the value of the constant everywhere, including across assemblies. So if let's say you define this constant here, and we see an example, you define this constant in this class / assembly here, but the same constant is being used in 15 other assemblies. At compile time, that constant will be baked into the call site across the assemblies. But there's a problem to that. You have to be aware of this problem. Okay, I'll get to that. But notice also that the way we wrote the code here that's calling this method that has a default argument value, that has also been baked into the call site. Right, so even though we didn't specify the 5, at compile time it has replaced that nothing with the 5. Right, so that's how that language feature has been introduced in C#. I think probably like 4 or 5 or something. We got this default arguments, default parameter values feature. It's doing the same thing. It's like a constant. It's not a constant, but in terms of the lowering aspect, it's like a constant. It gets baked at the call site. If that call site is across another assembly, it'll get baked at the call site there too. Now the problem can occur when, let's say you change this assembly. If I were to change this to 200 here, you would see that and not rebuild all assemblies, all dependent assemblies. This application will work just fine with this constant and this value, but you might have a bug, if you will, because you didn't recompile all other dependent assemblies. They still have to have the old value baked into the call sites there. So that's something you have to be careful about with constants and with default parameter values. All right, but I want to show you again the lowered version of that. So we saw that part. Okay, next up we'll look at, what should we look at? Delegates. Now I had a video recently on delegates. You might want to watch that if you don't understand delegates. I'm not going to explain delegates, but I'm going to show you the kind of the lowered version of the code for delegates. So if I have some code over here, let's say this, and I have this method here, that's it, that has this delegate signature, and that method's implementation is here. Then let me see what happened if I were to see the compiled code for this. So I'm going to just take this into SharpLab to see if I can show you something useful there. Okay, what do we see here? So you don't see much because you're not even seeing the delegate itself, which should be a class. You're seeing this as the same thing. Nothing has really changed. But let's look at the IL then. If I look at the IL for the delegates, Then you're going to see one. You're going to see there's a whole another class here. There's a whole class called display formatting delegate that is a descendant of multicast delegate and so on. So what we don't see when we use delegates is each delegate is actually another class, and effectively the invoke method is called when the delegate is called, and in the main method it's going to call that delegate just like we have right now, right? So that won't change. Well, and as I mentioned in the delegates thing video, that this is nothing but a call like this is nothing but say new up an instance of the delegate passing in the method as a constructor argument, right? So you can see that over here, and then it's in debug mode, that's what you see, but at release mode you'll see that it disappears, but that's like an optimization. It still has the class and everything else is still there. It's not like it's not there. Alright, so that's the delegates. Now some other things here I want to show you, like this concatenation, right? So if I look at this concatenation, what if we use the new currently in SharpLab, as you can see here, it's simply, it hasn't changed it. But let's look at the IL for this part. So I'm looking at now the concatenation here. So we open up let's open up this method here. All right, so you can see that it's calling, oh yeah, it's calling the toString on the int, and then it's doing a string.concat. So it's calling the string.concat method with string. So it's using there's many overloads to this concat method, and it's doing a string method. It's using the overload that has string arguments rather than object arguments. All right, which is actually a good thing. So this is actually the most optimal way of getting there. Is hopefully your compiled code is calling string.concat, and the overload is also using the string version. I'll show you what would happen if you change the code to where you think it's better, because you got this new feature in C#. We would prefer to do something like this, isn't it? Seems pretty reasonable. After all, it's a new feature and looks really cool, doesn't it? Let's build this and then look at the IL for this as well. So all right. Oops, there's a few problems here now. One, the int that we had got boxed. So anytime you see the box instruction like we do over here, that's a problem, right? If you don't understand unboxing, then please take a look at, I don't have a video on it, but kind of do a Google search and figure that out. Box indicates something is being boxed, and of course it's that integer that we had that is now being boxed, plus the string.concat has now changed to a string.format. And this is a very heavy method. It's a very slow method. You should use string.format for things that you intend for formatting, like culture sensitive things, maybe date times are being converted to strings and such, numeric things. That's when you want to use string.format. Don't use string.format for every single time you want to concat. Better use a string.concat, or just leave it like it was before with the plus signs. You're not adding any benefit. Now, there is a time when this thing would actually use the string.concat behind the scenes, but it's not. I haven't figured out when it decides to do that, but when it's not. But most times it uses string.format. So you might think this is cleaner code, and I'm not saying you shouldn't use this. if your system is extremely sensitive to performance, you're trying to squeeze out all the performance you possibly can because you are not meeting your performance requirement, then this may not be a good choice. Leaving it alone the way it was before is probably a better choice, including the toString on this rating thing, because this is preventing the boxing of the int, and it's a string.concat. Right? So that's what I want to show you. In addition to the delegates, I want to just show you some of the other stuff that's going on behind the scenes, the lowering from the perspective of the new features with in C# that we called interning, string interning. Right? It's not a runtime feature; it's a compile time lowering feature. All right. Next up, extension methods. Let's pick this one. This is also very simple. So we know extension methods, and you know my opinion on those since I made a video recently on extension methods. So here's the class that is extending this iDisposable, and it's dispose if not null, and that's the logic here, and I use it over here. Right? So I new up a stream and I dispose if not null. And all I want to show you here is like what is the compiled version of this. And I don't know if ReSharper will show it like this. Let's see what, not ReSharper, I mean SharpLab. Yes, so this is cool. So in SharpLab you can see, even though we wrote the code like this, what the compiler lowers it to is a call to this class dot this method, static method, and sending this disposable as an argument. So that's all extension methods are. They're just convenience, if you will, syntax. Of course, there's other issues, as you know, that I mentioned in the other video on extension methods, but from a loading standpoint, that's what's happening. Well, that was simple. What's next? Okay, next up, I want to just show you or talk to you about for each. I've got a simple piece of code here, and I'm just going to take all this and put this into SharpLab. So immediately you'll see that there are some things that have changed. The way the array is initialized, we write this simple syntax like this, but basically it has to use an array initializer to initialize the array. So it's not sort of magic, it's lowering, essentially writing the code the way we would have normally written it in this fashion. Now, as I said, SharpLab is not doing the right job here. It's not. Its intention is not to show a lowered code. So it's not like it's trying to show a lowered code. It's doing its best to reverse engineer, if you will, or use the newer compilers to show you the C# code. But if you look at the IL, you'll see that even this will actually be separate lines of code to initialize the arrays, 0th element and first element, and so on and so forth. And the for each here is actually not written like this. The lowered version of for each is slightly different. What if we were to change this to a list instead of an array? Let's say it's a list of int. Right, compile this. Or you could just take this into SharpLab. Actually, I could have just changed it in SharpLab itself. You'll see that it initializes, even though this is allowed in a C# syntax perspective, it actually has to lower the code to do this line by line. And the for each has now changed to a try finally. And that's the reason is that the for each is really using a numerator, and the numerator is a disposable, so it has to dispose the enumerator. Now, if you were using something inside of the for each that is not a disposable, then the compiler would not have written the try finally, right? So this is sort of part of lowering. Now, of course, for each has been in C# language since day one, and so as I said earlier in the beginning that lowering is not a new idea. It's been in C# since the beginning, but they've been utilizing more and more of the features of lowering to give us more language features. Now, for each is actually another special breed, if you will, of things in C#. what can you for each over? Now, normally you think anything that's an enumerable, you can for each over, which is true, but it's not completely true. What for each requires is anything that has the get enumerator method on it. It doesn't need you to implement the enumerator interface. There's a IEnumerator interface, there's an IEnumerator of T interface, there's an IEnumerable interface, and the IEnumerable of T interface. But the enumerator, let me show you. So let's say I have a class here. Let's call it policies. Let's say it potentially has a collection of policies, and I want to be able to iterate policies, right? So I want over here, let's say I say for each item in, say, policies, right? So and I want to be able to iterate over my policies. So you see it puts a squiggle here saying, I don't know what the heck you're trying to do here. That's because it's not seeing the get enumerator method on this. So let's put in the get enumerator method to this class. So it has to return a enumerator. For now I'm just going to say void. And let's say this returns. I'm not going to implement the whole thing, but I will just show you how this works. So let's say we have a policy. This returns an enumerable, so we'll have a policy enumerable. Sorry, this needs to be policy enumerator. Sorry, not enumerable. So here I'll return enumerator. All right, still not happy. The for each is still not happy. You can see still putting a squiggle here. That's because the enumerator itself, this class, needs to have a move next method on it and a current property on it. Enumerators also have another method called move next, current, and reset. Reset is never used. In fact, most implementations will throw an exception. So we just had the move next method returns a bool. So this will be public bool move next. Let's not implement it, but we'll return true for now. And the current property, the current should return a singular policy. So does a policy. We don't have a policy. Let's also define policy class. Okay, it's got the current method on property on it. It's got the move next method on it. Returns a bool. We're not implementing it, but it just sees the signature. At this point, the for each is happy, right? So the for each only requires, doesn't require you to implement the IEnumerator and IEnumerable interfaces. It simply needs, I don't know what they call this. Is it structural typing or pattern matching? I think it's pattern matching. So basically the for each is just doing a pattern match. Right? It's almost like it's duck typing, but it's pattern matching. Well, you could call it duck typing too. It makes no difference. I'm guessing the C# compiler team will say, no, it's not duck typing. Because C# is a strongly typed language. So I just want to show you that. So it's not a loading aspect here. It's just a language the way the language has been implemented, or the for each has been implemented in C#. All right. So, and of course, this will still have the try finally. So for each results in a, if I were to write this for, let's say, an int again. So let's say, okay, that's our collection. Instead of the way, when we write a for each in our code, the load version of that, it's really get enumerator. So this will be numbers dot get enumerator that returns a number enumerator. And then it does a try finally. And here it'll have a while number enumerator dot move next. And once it's able to move next, inside of here, it'll use the number enumerator dot current to get that value, the current value, right? So this will actually be the number, and then it'll replace whatever code you had in your for each on top of all of this. But as I said before, if the enumerator were disposable, then it would dispose of it. In other words, if you were dealing with, let's say, reference types, then this would be disposable and so on. So, and I think in SharpLab, I've seen the while. You know what? Maybe if I made this a list of, and see that's now becomes a reference type. Oops. And let's say I just make this a try for each. Okay, don't need all of this now. SharpLab. Yeah, so now because we're using a list, it'll dispose of it over here, right? So that's how it does the get enumerator. It then does this and replaces the rest of the code that you might have had in your for each into this part, into the while part, and dispose of it. So for each it will be converted to a while. It'll also have a try finally if the thing you're working on is a reference type, or anything that's a disposable. It doesn't have to be a reference type, only anything that is disposable. It'll have the try finally for the dispose. That's the for each. All right, next up we have the iterator. Now the iterator is a very interesting concept. The iterator pattern, it actually helps us implement the iterator pattern. And let me just also make this the current starter project. Okay, so if I look at this code here, this is, I don't know if you've seen this before, but it's really, this is like really intense. If you debug this code, try it out. If you haven't debugged your code here, try this out. It's super cool. It's mind-bending how the debugger provides a debugging experience that is intuitive, in the sense this is how you want to think about the yield return, but it's implemented as a state machine. I'll show you the state machine that's implemented. Let's copy this and paste it into SharpLab. So this little code here gets converted to a completely different class. This is an entire class that's being generated, which is the state machine. And then here's our code here. Now, because again, we are doing the enumerator, it's still doing that move next, try finally, dispose, if not null, all of that, right? Because it doesn't quite, because it's an enumerator. But this class here, this is what we call the state machine. and it's a nested class, as you can see here. The name of the class is going to be weird because this is a generated class, so you're just going to start with some weird things. This class implements enumerable and numerator, so it's doing the sort of double duty of both things. And you can look at this code. This code actually will not compile in Visual Studio because, as I said, the C# compiler itself will not allow you to write code like this with these funky names. But if you were to change these names to more sensible names and then compile this in Visual Studio, this will work just fine. And the state machine here, mainly this switch case, the move next method, is the state machine, and it basically sets the state to the first one is a -1, and then it the state, the current, and this state. So essentially, the state machine is allowing the code to maintain the state. That's what a state machine is. So as the state changes, the outcome or the output can change, and the ureturn that we write like this ends up being this massive class like that. So in other words, this is a instance of some object that eventually has to be disposed by the garbage collector. So again, when you use this new feature, you don't necessarily know this to be creating a whole nother class that also has to be disposed at some point. And it's got a switch case statement. So the state machine is implemented by way of a switch case statement. So it's a conditional, if you will, right? It's not just simple lines of code. So now there are benefits. In fact, in C#8, they've added a new feature called streaming, async streams. So till to date, we are not able to combine async methods with ureturn. It was either one or the other. And the reason is pretty cool because the async feature in .NET came after the ureturn or the iterator feature. And Jeffrey Richer, one of the authors, is a very well-known personality in the C# community. He's written a few books. The more famous ones in the .NET world are CLR via C#. It's a big thick book like that, and there's many additions to it. He was playing with things with ureturn, and he essentially implemented what we call Async-Await today using iterators. But then he took that to the C# team and showed them what he had, and of course the C# team then made it a language feature by adding a library and a bunch of other things, modified the C# compiler to then give us Async-Await. But if it weren't for him doing that initial stages where he worked with the ureturn, we may not have had Async-Await. And now in other languages like JavaScript and a bunch of other languages have supported are starting to implement Async-Await as well for IO-bound workloads. So the ureturn was the precursor to Async-Await, but because they're so similarly implemented, it was very difficult for them to support an async method that was also using the iterator pattern. Now in C#8, they support that. In other words, they're allowing us to use both Async-Await and iterators in the same method. I'll show you now how async gets implemented. Now there are some things to be careful about, as I said here. You don't want to have, if you can't afford, for performance reasons, to have additional objects being created, because those additional objects have to be garbage collected, and that is costing you. So don't just assume this is going to cost you and therefore try and do something to not use it, right? So performance should always be something that you're doing because it is costing you and you can't afford to have it. So I'm not saying you don't use ureturn. It's actually a very cool feature and I use it. But when I find that performance is costing me, then I will start to see what I can do to not do it in some cases, which is why lowering this video is important, because if you understand what's happening behind the scenes, then you know where to look when you have performance issues or other kinds of weird issues like boxing and unboxing and stuff like that. So now Async-Await, I mean. This is a pretty cool feature. Simple method. I've kept it very simple. I'm not actually doing anything asynchronously. I'm faking it. Please don't do this. This is terrible. This task.from result. You're faking. You're lying to me. I say you're lying to me. Don't lie to me. This method is asynchronous when it's not. But let's pretend that this work was actually doing some IO-bound workloads here. I wasn't actually using task.from result, but I was awaiting something here. Let's look at the code here. The code that's generated by SharpLab. I think SharpLab, yeah. See, I've left myself a comment here. It says show in SharpLab. All right. So this method getData has been converted to this whole async builder or method builder class. Let's say you can see it's an iAsync state machine, or it implements iAsync state machine. It's a huge amount of code, right? And then we have the getData, which is the state machine itself. That's a whole other thing. That's a whole lot of code. And then finally, we have our getData method and the actual main method, right? So we wrote literally this. We wrote this code, and that got converted to two methods that are state machines, if you will. One for the getData method, which is an async method, and one for the sort of the main method, but basically it's the same idea, just the sort of repetition of the same thing, right? So these are massive classes. Nothing wrong. I'm not saying don't use async. You should be using async if it's IO bound, but async is not about performance, it's about scale. If you don't understand what I'm saying, please look at my async video. You should use Async-Await for IO workloads. There's a cost to it, but as long as you can amortize that cost, meaning if you're calling that method often enough, but the cost of the overhead is amortized, then you can justify it, right? I just want to show you the lowered version, the sort of the generated code that C# compiler produces in this scenario. Now there's a common practice, so not a common practice, but a common place where people make a mistake with Async-Await, and I'll just highlight it over here since I have the code available. Look at this method here. The very last thing, I assume there's 20 lines or whatever code ahead of this, on top of this. The very last line of code is an await. This method says, signature says, you need to return to me a task of a string. Okay, I have a task of a string, and it says it's asynchronous. And this thing is then awaiting this method as well, because this method is async, this method has to await it. If the very last thing you're doing in an asynchronous method is simply returning await and return, like I'm doing here, return await. In other words, this method is not interested in the result of the await, then don't await it here. So now I'm going to take out this await. As a result, I have to take out the async. The call side is not impacted. See, the call side has not been modified one bit. But this method's signature has changed. It's not the signature, but async modifier has been removed. And I've removed the await here. I'm going to rebuild this. Oh, I don't need to rebuild. I can just take it into SharpLab. And let's look at what SharpLab does this time. So you'll see that we still have the main method's state machine, right? And then we have our main method and the getData method. Look at this getData method. It's the simple thing here, much simpler than before. The idea is this. For every method that is marked with the async modifier, you're going to get a state machine. So if you can, even though you're doing things asynchronously, you may not need to await the result in the method. So if you can avoid doing an await as the very last thing in your method, because you're not obviously using the result, you're returning, you're saying return await something, you don't need that result value in this method. The calling method wants it. Don't mark that method with the async modifier. The signature is still the same. It still returns the task. You don't have to await it inside. Don't mark the method with the async modifier. That if you do that often enough in a bunch of places in your system, you could potentially be saving yourself a lot of memory utilization, garbage collection, performance, and so on and so forth. All right, I think that's the end of that. And this is quite taxing for me because I have to remember which project, what am I trying to show, and I'm sure I missed a bunch of things that I had planned to show. But I think you get the point. I hope you get the point of lowering what it is and what the benefits are, especially if you're at a certain level where you're wanting to know what's going on under the hood. You want to see what code is generated, and if you're having performance issues, you can use this knowledge to then figure out where should you be looking, and does it truly get you any performance benefit or not. But that's performance is all about testing before and after. Don't ever assume performance. All right. Anyway, that brings me to the end of this one. I hope you enjoyed it. If you haven't already subscribed, please subscribe. Please give me a like. Please give me the thumbs down if that's what you want to do. If you do give me a thumbs down, all I can ask is, please tell me why. The only way I can improve is if you tell me why you don't like something. By just saying you don't like it, I have no clue, right? I'm sure people make blunders, but if you can tell me why, then at least I can see, try and prevent that. Either ways, I will see you all next time.